Hello. Today I will be going through your Unit 1 review over limits and continuity. So the basic rule with limits is if you're going to a specific value, plug it in and see what happens. So here if I plug in 7, we get 3 times 7 minus 1. So 21 minus 1 is 20. Here, if I plug in 1, we're going to have 0 over 1 squared plus 1. So 0 over 2, which is 0. Versus the second one, which is the same thing, just flipped over. So this is going to be 2 over 0. And if we have 2 over 0, that is undefined or does not exist. In fact, there will be a vertical asymptote there. Okay, here, if I plug in 1, we're going to have 1 plus 3 minus 4, so that's 0. And if we plug in 1 in the bottom, that is also 0. So if you have a 0 on the top, it's 0. If we have a 0 on the bottom, it's going to be undefined. But if we have 0 in both, this is indeterminate. In a case like this, oftentimes our strategy will be to factor. So we're looking at this. This is going to factor to x plus 4 times x minus 1. Then in the denominator, difference of two perfect squares. And there we go. For 5, 6, and 7, we're not going to a value, we're going to infinity. These are all rational functions. So what we're going to look at is the degree. So the degree on both the top and the bottom here is the same. So it's going to behave like the ratio of the leading coefficients. So as we get bigger and bigger and bigger, the 4x squared and the 5x squared are going to take over, and it will simplify to 4/5. In number 6, we have a degree 2 versus a degree 3. So degree 3 wins. So it's bigger on the bottom, which means the denominator is going to grow faster and faster. So we're going to go to 0. This one is the reverse of that, where my degree is bigger on the top, which means the numerator is going to be growing faster. So it's going to go to infinity or does not exist. These next three, we have the same function, x over x plus 2, and we're approaching negative 2. We know there's going to be a vertical asymptote there, but we're going to do some investigations on the right-hand limit and the left-hand limit. So if I plug in 2, negative 2, so we're going to plug in negative 2 over negative 2, and I'm going to put a little plus here, plus 2. So looking at numbers as we got really close, if I'm plugging in numbers that are just a little bit bigger than negative 2, that means this denominator is going to be positive, but the numerator is going to be negative. So this is going to go to negative infinity from the positive side. Okay, if we approach it from the other side, we're going to have negative 2 over negative 2 minus. So if I'm plugging in numbers that are less than negative 2, then this is going to be a positive value, or sorry, a negative value. So we get a negative over a negative, which is positive. So this is going to go to positive infinity. But if we were not asked for the one-sided limit, we were just simply asked what is the limit as we go to negative 2. That limit does not exist. We're going to positive infinity on one side, negative infinity on the other. There's a vertical asymptote, no limit. Okay, these next two are just ones that you want to have memorized. So we've looked at this graph. I'll remind you of what the graph looks like. Okay, graph as it approaches 0 is going to be at 1, and then as we go to infinity, as the denominator here gets bigger and bigger and bigger, because sine of x is between -1 and 1, the denominator is going to grow, so it's going to approach 0. So as we go to 0, we're going to 1, and as we go to infinity, the graph is approaching 0. Okay, this next one, we have sine of 1 over 0. So this thing can be pretty much any value between negative and positive infinity. But we're taking the sine of it. And really from the beginning, we could have said this. But this is either going to be between negative 1 and 1. Okay, or what we call a bounded bouncer. But because it's not approaching one thing, this limit does not exist. However, if we plug it in here, we're going to have 0 times something that is limited. Okay, it will never be between, it'll be between negative 1 and 1. It's not going to be bigger and it's not going to be less. So if I'm multiplying by 0, that will be 0. All right, so we know that the limit as x goes to 0 of sine x over x is 1. So what we want to do here is change this problem so that it looks like that. So I'm going to multiply by 4 over 4. So that gets me the limit as x goes to 0 of 4 sine 4x over 4x. So this part here is essentially sine x over x as long as they're the same. So what we have is 4 times this limit is 1, so we get 4. Okay, these last 4, I'm going to again look at the graph, or think about the graph. Okay, so this whole thing is going to be undefined at negative 3. If I plug in a number bigger than negative 3, if I plugged in 4 or 5 or 6, you're going to end up with the same thing on both the top and the bottom. And if you have the same thing over the same thing, that is 1. So I'm going to put an open dot here, like that. Now as I approach it from the negative side, they're still going to be the same value, but the top is always going to be positive and the denominator is going to be negative. So for the bottom, it's going to negative 1. So that's what the graph looks like. So as we approach x equals negative 3 from the negative side, we're going to negative 1. From the positive side is 1. And then the last two are negative infinity and positive infinity. So negative infinity is going to negative 1. Positive infinity is going to 1. Okay, so for this one, plug this in. We'd get the square root of 49 is 7 minus 7, so we get a 0 in the top and a 0 on the bottom. Sorry. As we plug in 49, we get 0 and 0. Okay, which means we need to do more investigation. This time we're going to use conjugates. So I'm going to multiply by the square root of x plus 7 over the square root of x plus 7. When we do that on the top and FOIL, so I'm going to keep the word limit here for a little bit. So the limit as x goes to 49. If I FOIL, so x squared, the square root of x squared times the square root of x squared is x. Then we'll have plus 7 root x minus 7 root x. And then negative 7 times positive 7 is a negative 49. On the bottom, I just have x minus 49 and root x plus 7. We're going to leave it like that. Well, this top, these middle two go away, and that's the whole point of the conjugate. So as we go to 49, we have x minus 49 in the top, x minus 49 root x plus 7. So the factors reduce. And I'm going to show all the steps just so we're real clear. Okay, because it's tempting to say, well, that's all that's left, but it's really 1 over that. So I have 1 over the square root of 49 plus 7. Well, the square root of 49 is 7, so this ends up being 1/14. Okay, this one looks similar, except for we are going to infinity. Well, this is the square root of x, this is the x. So this one has the higher degree. This is degree 1, this would be degree 1/2. So since it's bigger on the bottom, this is going to go to 0. Okay, these exponentials, we want to look at what happens as we go to infinity and negative infinity. Well, e to the x looks like that. So as we go to infinity, we're going to have 4, I'm just going to say plus infinity, and 4 minus infinity. Well, these are going to be growing at the same rate. So they're going to go to, it's essentially going to be the same thing over the same thing, but they're opposite signs. So this is going to be -1 because they're growing at really the same rate, but this one's negative. As we go to negative infinity, e to the x goes to 0. So what takes over are those constants. So this is actually going to go to 4/3. Okay, for piecewise, we just want to look at what's happening where we're looking. So A is what is the limit as x goes to negative infinity of f of x. So we look at these bounds. This is the equation that's going to exist there when we go to negative infinity. So this we want the limit as x goes to negative infinity of this, which has the same degree on the top and the bottom. So this is going to be just the ratio of the leading coefficients, 3/2. For infinity, now we're looking at this. This is going to be the limit as x goes to infinity of 1 over x plus 2. Well, if we've got a bigger degree on the bottom, this is going to go to 0. Okay, now we're going to look at -2 from the negative side and from the positive side. So this will be the limit as x goes to -2 of the first one again. So that's going to be 3 times 2 plus 1 over 2 times 2 minus 3. -2, sorry. So we've got a -6 plus 1 is -5. -4 minus 3 is -7. So this is 5/7. As we go to -2 from the positive side, then again we're looking at that second equation. So this is going to be 1 over -2 plus 2. So if we're plugging in numbers just a little bit bigger than -2, then this would be, it's going to be positive, which means it's going to go to positive infinity. If we had come from the other side, it would have been negative. Okay, so we're going to sketch a possible graph. Now keep in mind there's different correct ways to draw this graph. This one's asking for if f of -2 exists and the limit as x approaches -2 exists, but it is not continuous at -2, And then at x equals 1, the limit does not exist. All right, so at -2, if we have the limit exist, that means it's going to the same thing from both sides. Again, your graph can look like whatever. But the function value which exists is not going to be the same. So the limit exists, the function value exists, but it is not continuous. At 1, it just says the limit does not exist. So that's easy to do. Okay, just make it so that there's some sort of jump there. All right, now we're going to be using some properties and a table. So we have A, we have the limit as x approaches A of f, and G, and our different values of A. Well, if we're looking at the limit as x goes to 2 of f of x over g of x, that's just going to be the limit as we go to 2 of f and g. So at 2, f is going to -2, g is going to -4, so that's going to be a positive 1/2. Okay, this is going to be 2 as x goes to 0 of f of x is -1. And g of x is 3. So -2 plus 3 is a positive 1. As we go to 6 of g cubed, 6g, this is -2 cubed, which is a -8. And then for this one, as x goes to 4, so we're going to plug 4 in for the x, and then the limit as x goes to 4 of f of x, which is 5, and then 2 times the limit as we go to g of x, we have 9 over 4. So just using those properties. Okay, for number 22, if f of x is x and g of x is 1 over x, so explain why the rules do not apply if I wanted to do f times g. Well, if I just did f times g, that's going to be, we could figure out each limit individually, but if I just multiplied x times 1 over x, well, that's just 1. But that's not what f times g of x is going to look like. So why doesn't that work? Because the limit has to be finite in order for this to apply. This one is finite as we go to 0, but this one as we go to 0 is going to be infinity, which is not finite. So the limit as x goes to 0 of g of x is infinity, which is not finite, which is required for the limit rules to work. Okay, horizontal and vertical asymptotes. Horizontal asymptotes are obtained by looking at the limit as x goes to infinity of our function. So x squared plus 7x plus 12 Okay, well, we're looking at the degree. The degree is bigger on the bottom, so this is going to go to 0. So we have a horizontal asymptote at y equals 0. Vertical asymptotes are going to occur in what makes the denominator 0 unless it is a point of discontinuity. So to do that, we're going to want to factor. Top's just going to factor to x plus 3 and x minus 3. Here, I can pull an x out, which will leave me with x squared minus 9, which can factor to x, this would be plus 4. I was looking ahead. X plus 3, x plus 4. So this is going to be x plus 3, x minus 3. Okay, so we do have a point of discontinuity at x plus 3, so there's no vertical asymptote there. But anything that makes the denominator 0 with what remains is our vertical. So we're going to have one at x equals 0 and when x is equal to 3. Okay, using the definition of continuity, determine whether the function is continuous at 1 and 3. At 1, clearly not continuous, so this one is discontinuous. Or I'm just going to say, no, it is not continuous. The reason being, it's going to 2 different places. So the 3 things that has to be true, it has a function value, but it does not have a limit. Okay, for x equals 3, it has a function value. The limit here does exist. It's going to the same thing from both sides. However, those are not the same, so it fails the third part of our continuity test. So we can just state that as f of 3 does not equal the limit as x approaches 3 of f of x. For C, it says what new value should be assigned to f of 3 to make it continuous? Well, if we want this to be continuous, then I need that hole to be filled. So we want 2, and if we can do that, if we can assign a value and suddenly it's continuous, this is called a removable discontinuity. All right, part 2 of your exam will be calculator allowed. So we're going to use the calculator to make a table of values to estimate the limit as x goes to 0 of tangent of x over x. So I'm going to put 0 in the middle here, and you can pick values that you think would work. I'm just going to go by tenths, so negative 0.1, negative 0.2, negative 0.3. You could go by hundredths, just as long as we can see what's happening as we get close to 1. Okay, in our calculator, in my y equals, we're going to put tangent of x over x. You always want to make sure that you are in radian mode for calculus. So then I'm going to go to my table set. I'm going to start at negative 0.3, and I'm going to go up by 0.1, just for the values that I selected. If you pick something different, that's fine. So then I'm going to go to the table, and these are my values that I'm going to copy down. So here are my values. So we're going to look at the table to determine what's happening here. Well, these values appear to be approaching 1, and these values appear to be approaching 1. So since those are the same, we say that that limit is probably 1. And if we go to the graph, okay, sure enough, at 0, it's approaching 1. It's going to be undefined there, because if I plug in 0, we get a 0 in the denominator. But the graph confirms it. Okay. The intermediate value theorem. Okay, if a function is continuous, I'm going to draw a picture to help us illustrate. It says write two statements that might be true and write two statements that must be true. So there's going to be a slight difference between these. We're given that f of negative 10 is 4, and f of 10 is negative 4. Okay, so this is what we know to be true about the graph. So I could graph it like this. I'm going to draw 2 of them. Okay, so we've got our 2 points that we know are on the graph. Let's say I go like that this time. Okay, it's continuous. We have to connect this point to this point. But here I'm going to say f of 0 is 0. Here I'm going to say f of 0 is 3. These are things that could be true. They don't have to be true, because obviously I drew the graph 2 different ways. So it might be that way. What must be true is that somewhere between negative 10 and 10, it has to pass through 0, and it has to pass through 3. If it's going to go from this point to this point, every single y value must be represented. Okay, so what must be true, and this is just an example of what must be true, f of c must equal 0 at some point between negative 10 and 10, since 0 is in between negative 4 and 4. So I could draw this graph a lot of different ways. Okay, it hits 0 a lot, but at least once it needs to hit 0. Okay, and then you're supposed to write 2, so you can write your second one. You just pick some other value here where it's between -4 and 4. Okay, if a function f is continuous on the closed interval 1, 4, if f of 1 is 6 and f of 4 is -1, which of the following must be true? Okay, I'm going to go ahead and sketch this. I think that's helpful. Okay, so we are told f of 1 is 6 and f of 4 is -1. So blah, blah, blah. Okay, we have to go from here to here. And then we kind of have these f of c equals 0, f of c equals 1, f of c equals -1. So the first thing to look at is what interval are we interested in? We want from 1 to 4. Okay, the other ones are giving us the y values, which isn't true. Okay, so that one's out and that one's out. So now let's read what it says. This says f of c equals 1. Okay, well that's true. But let's take a look at D. F of c doesn't equal -2. Well, the way I drew it, it doesn't equal -2. But you could have, and it dips down and then comes back up or whatever. So it must hit every number between -1 and 6, which includes 1. It could still go outside of that. And then it's only on when the x's are between 1 and 4. All right, the functions f and g are differentiable, which we'll get to later. So there's two columns here which we have, but we are not going to be using at this point in time. It's strictly increasing. Again, that's something that we'll care about later. The table above gives the values of the functions for the first derivatives. Don't care, but the values of the functions what we want. H is equal to f of g of x minus 6. Then it says, explain why there must be a value of r for 1 is less than r is less than 3, such that h of r equals -5. Well, this is just asking you to complete the intermediate value theorem. So what I need to do is evaluate h of 1 and h of 3. Okay, and it's probably a safe bet to say one's going to be bigger than -5 and one's going to be smaller than -5. This is going to be f of g of 1 minus 6. Now we use the chart. So g of 1 is 2. F of 2 is 9. And 9 minus 6 is 3. H of 3 is going to be f of g of 3 minus 6. G of 3 is 4. F of 4 is -1. So that gives me a -7. So I'm going to write out the intermediate value theorem. So our statement, since h is continuous, we have to stay that. And for this problem, we're told it's differentiable, which is going to imply continuity. We will get to that soon. But so since it's continuous by the intermediate value theorem, which you can abbreviate as IVT, since h of 3 is -7 and h of 1 is 3. Now we did that over here, so you don't necessarily need to include that, but you should have this part that -7 is less than -5, which is less than 3. There must be some r such that h of r is -5. So the pieces they're looking for is continuous by the IVT, and that it's between here. Okay, so for which of these functions does the table suggest that the limit as x approaches 0 exists? The first thing I want you to do, cross that off. I don't care what happens at 0. I just care about what happens as we get really close. Okay, so let's look at f. So the limit as x goes to 0 from the negative side of f of x. So these values are approaching 0. They're getting smaller. What about from the positive side? Okay, these values also getting smaller. So they're both going to 0, even though that's -4. Don't care about that. Okay, so that one is going to work. So f of x, yes. Okay, let's look at g of x. G of x. So as x goes to 0 from the negative side, these are approaching -8. Okay, as we go to the positive side, -8 again. So this one works. Okay, if we look at h of x, and you don't necessarily need to do all of this work, I'm just emphasizing what's going on. I wrote down negative, positive. From the negative side, we're going to 2. From the positive side, we're approaching 1, which is not the same, so this limit does not exist. So f of x and g of x only. Okay, explain the meaning of the limit as x goes to infinity is 2. This means that there is a horizontal asymptote. At y equals 2. Here, explain the meaning of as x goes to 3 from the positive side goes to infinity, and 3 from the negative side goes to negative infinity, means that there is a vertical asymptote. At x equals 3. Okay, so we've got this piecewise function with some a's and b's. It says if a is equal to 4 and b is equal to -1, is f continuous? Well, where we're concerned is at 3. So I'm going to look at the limit as x goes to 3 of this one with the value they gave us plugged in, so 2x minus 1. Well, that's going to be 2 times 3 minus 1, which is 5. Then I'm going to look at the other one as it goes to 3. So a is 4, so this is 4x squared minus x. So that's going to be 4 times 3 squared minus 3. So 9 times 3 is 30, or 9 times 3 is 36, minus 3 is 33. Okay, so is this continuous? No, it is not. Okay, because the limit as x goes to 3 does not exist. Okay, so where would the values be continuous? Well, the values are going to be continuous if I plug in 3 and I get the same thing. So if I get 2 times 3 plus b is equal to a times 3 squared plus b times 3. So you can write this in different ways, but that's fine. Okay, for C, let A equal -3, find the B, and show that it's a continuous function, and then we're going to graph. So if A is -3, I'll plug that into this equation and use that to solve for B. So this is going to be 27 plus 6 is 33. So B is going to be 16.5, or you can do 33 halves if you want. Okay, so that means my f of x is now 2x plus 16.5 when x is less than 3, and -3x squared plus 16.5x when x is greater than or equal to 3. So we can show that these are continuous by looking at each of those limits. So if I plug 3 into this one, we're going to get 22.5. Remember, you get a calculator for this part. X. Okay, if we plug 3 in for this, you'll also get 22.5. So you can use a calculator to help you out with this part. We're going to have this line that's going to lead up to 3, and then after 3 we've got this upside down parabola, so it ends up looking kind of like this. Our last question is getting us ready for our next unit. So we have this equation. The slope of the secant line is just y2 minus y1 equals, or y2 minus y1 over x2 minus x1. So 13 minus 4 over 2 minus 1. So that's going to be 9 over 1, or just 9. The slope of the secant line, okay, we're going to take the 13 and the 2 and replace it with f of x and x. Okay, so then I'll replace this for f of x. So f of x minus 4, so this minus 4. So this is 2x squared plus 3x minus 5. Okay, well the slope of the tangent line is going to be the slope at 1. So if you picture the secant line going through 2 points, we want that point to be as close to 1 as possible. So it's going to be the limit as x goes to 1 of this slope formula. Okay, well, we need to factor. And we know x minus 1 has to be one of the factors if this is going to simplify. So that's going to give me a 2x plus 5 to get that and that. So these will cancel. So we've got 2 times 1 plus 5 is 7. And again, you've got your calculator to help you with the graph. Okay, so we've got the graph. It's going to go through, when it's 0, our parabola is going to be at -1. We know at 1 is at 4 and 2 is at 13. And again, you've got your calculator to help you. So it's going to look something like that. The secant line is going to be the line that goes through these 2 points. Okay, and we'll pretend it actually went through that point. So this is our secant line. The tangent line touches at this dot and it just grazes it. Right, so that is Unit 1 review. Good luck on your test.